In line with other instruments, coloured arcs or indicator lines are used to show ranges and limits of engine speed. A green arc will represent the normal operating range, and an amber arc will denote a caution range. Red arcs show either the maximum speed of the engine or RPM ranges which are restricted, perhaps because vibration may be encountered within them. The glass cockpit uses a mixture of analog and digital displays on the same dial. This type of analog display is very useful in two ways. Firstly, for instantaneous comparison of multi-engine states, and secondly, the digital readout is a very accurate indication of individual engine states when they're required. If a parameter limitation is exceeded in the glass cockpit type of display, the whole of the dial displaying that particular parameter will change to either amber or red, depending on how far the limitation has been exceeded. On some older glass cockpit instrumentation, vertical ribbon displays are used. Many multi-engine aircraft are provided with a visual indicator, which is called a synchroscope, which indicates the RPM difference between the slave engines and the master. As you can see from this picture, the presentation consists of miniature propellers which rotate to show when an RPM difference exists, and whether the slave is faster or slower than the master. Gas turbine engines are heat engines. The power gas turbine engines produce is directly proportional to the heat released during the combustion of the fuel. Engine components and systems are designed to withstand certain temperatures. If their temperature limits are exceeded, they will fail. To allow safe operation, the engine temperatures must be monitored. The following temperatures are monitored on gas turbine engines: engine air inlet temperature, exhaust gas temperature, engine oil temperature, and internal air systems temperature. The temperatures monitored may range from minus 56 degrees Celsius to plus 1200 degrees Celsius. Different sensors are used depending on the temperature range to be monitored. There are 4 major types of temperature measuring device. They are the expansion type, which relies on the principle that most solids, liquids, and gases expand and contract with temperature changes. 2 examples of the expansion type of device are the mercury thermometer and the bimetallic strip. The vapor pressure type of device uses the principle that liquids, when subjected to a rise in temperature, change their state from liquid to vapor. By measuring the pressure of the vapor, an indication of temperature can be gained. A change in the temperature of some electrical conductors, for instance platinum, will cause a change in the electrical resistance of that conductor. Measuring the change in the resistance of this conductor will indicate its temperature. This type of sensor is called the resistance type or the temperature bulb. In 1822, Thomas Seebeck accidentally discovered that heating the junction of 2 dissimilar metals will produce an electrical potential that is a function of temperature. If the junction is contained within a closed loop, the value of the potential will be dependent on the difference in the temperature between the junction where the heat is applied, the hot junction, and the other end of the loop, the cold junction. Examples of the use of thermocouples include the measurement of cylinder head temperature and turbine gas temperature. A radiation pyrometer is a device which can convert radiated energy into electrical energy. It consists of a photovoltaic cell and a lens which focuses the radiated energy onto the cell. The pyrometer is positioned so that the lens can be focused directly onto the heat source, in this case the turbine blades. The photovoltaic cell converts the radiated energy emitted by the blades into electrical energy, which is passed through an amplifier to an instrument calibrated in degrees Celsius. The temperature of the gas passing through the turbine of a gas turbine engine is the most critical parameter of those displayed on the engine instruments. Operation of the engine beyond the limits of turbine temperature, even for only a moment, is liable to cause excessive turbine blade creep, which will be catastrophic if the rotating blades touch the casing of the engine. The gas temperature must be monitored closely, and automatic temperature limiting equipment is fitted to most gas turbine engines operating today. To enable this monitoring to be achieved, temperature probes are inserted in the gas stream. Temperature probes are formed from the junction of two dissimilar metals, which, as we've just seen, generate a potential when the junction is heated. The potential is proportional to the temperature applied to the junction. This diagram shows how the terminals for the connections to the probes, which are the hot junctions, are connected, and also how the gas flows over them. The output from the probes is sent to the cockpit engine instrument, which is the cold junction. Here the potential is displayed on a very sensitive millivoltmeter calibrated to show the engine gas temperature. A single probe would not supply enough information to accurately tell the pilot what was going on in the whole of the turbine. It could only inform him about a small part of the turbine that it was monitoring. Additionally, a failure of that single probe would rob the pilot of his knowledge of the most important of the engine parameters. To gain complete awareness of the temperature situation, it's necessary to place a number of probes around the periphery of the turbine or the exhaust system. The probes are connected electrically in parallel. Their output is thus the average of all of the probes. Connecting the probes in parallel has the added advantage that if one probe is damaged, their electrical output, and therefore the temperature reading on the gauge, is virtually unaffected. The position of the probes in the engine depends upon two things: the anticipated maximum temperature of the gas and the ability of the probe material to withstand that temperature. The industry standard for the material used at the junction in the temperature probes in gas turbine engines is chromel, nickel-chromium, and alumel, nickel-aluminium. These two materials may not have the highest millivoltage output of the materials available, but their ability to withstand very high temperatures, coupled with a reasonable volts per degree ratio, makes them ideal for the job. The system does not require a power supply for the gauges to work. However, if the potential generated by the probes is to be used to supply a temperature limiting system, the output will need to be amplified. The power required for amplification will be supplied by the aircraft's electrical system. If it's required that the probe supply both a temperature limiting system, otherwise known as a top temperature control, and a temperature indicating system, they will contain two separate junctions, one to feed the temperature limiting system and one to feed the indicator. On the type of engine where the temperature of the gas within the turbine is too high for the metal of the probes to stand it, the probes may be positioned after the turbine and the gauge calibrated to read exhaust gas temperature, or EGT. On other engines, it may be found convenient to combine the temperature probes with the pitot probes, which measure exhaust gas pressure, P7. In this case, the gauges will read jet pipe temperature, or JPT. Obviously, it would be ideal if the temperature could be sampled either before the turbine, when it would be called either turbine inlet temperature, or TIT, or turbine entry temperature, TET. Alternatively, the gas temperature could be sampled inside the turbine, when it would be called turbine gas temperature, or TGT. In every case, the position of the probes is dependent upon their ability to withstand the temperatures they encounter. Actual blade temperature can be measured by the radiation method, with the use of an optical pyrometer. Air temperature is one of the basic parameters used to establish data vital to the performance monitoring of aircraft engines, for example, thrust settings, fuel-air ratio settings, etc. The ideal temperature to suit these requirements is that sensed under static conditions at various flight levels. This temperature is called variously the outside air temperature or static air temperature, SAT. Unfortunately, this measurement can be affected by the adiabatic compression that occurs with increase of aircraft speed. Below 0.2 Mach, the temperature of the air sampled is very close to SAT. But at higher Mach numbers, an increase in skin friction will raise the air temperature. This increase in air temperature is commonly referred to as ram rise, and the temperature that's indicated is called ram air temperature, RAT, which is the static air temperature plus the increase caused by the ram rise. The ram rise can be computed by air data computers to correct the indicators to SAT, or alternatively calculated mathematically for each type of aircraft as a function of Mach number, and tables or graphs can be included in their flight manuals. For use in the instruments of aircraft which fly at high Mach numbers, total air temperature, TAT, is measured. The air is brought to rest, or nearly so, without the addition or removal of heat. Total air temperature equals static air temperature plus ram air temperature plus friction rise. Temperature indicators use coloured arcs to show their operating range. Green for normal, amber for caution, and red upper or lower limits. Pressure is defined as force per unit area. Pressure is normally indicated either as pounds per square inch or inches of mercury. When we're discussing pressure measurement, we must use the following terms: absolute pressure and gauge pressure. Absolute pressure is measured relative to absolute zero pressure, the pressure that would occur at absolute vacuum. Thus, the absolute pressure on the Earth's surface at sea level is the atmospheric pressure, which is 14.7 pounds per square inch. The more usual pressure measured by most gauges is called gauge pressure. Gauge pressure reflects an adjusted pressure that reads zero at the Earth's surface. Elastic pressure sensing elements are used to measure pressure. Forces are produced within the elements by applied pressures, and these forces are converted to mechanical movement. The mechanical movement is then used to operate either a direct reading gauge or an electrical transmitter. The sensing elements commonly used are diaphragms, capsules, bellows, and Bourdon tubes. A diaphragm is a sheet of a semi-flexible material, anchored at its periphery, and most often round in shape. It usually serves as a barrier between two chambers, moving slightly into one chamber or the other, depending on differences in pressure. Diaphragms are used to measure low pressures. Capsules are made up of two diaphragms placed together and joined at their edges to form a chamber. The chamber may be sealed, in which case the device is called an aneroid capsule, or it may be joined to a pressure source, in which case it's called a pressure capsule. Like diaphragms, capsules are also used to measure low pressure, but capsules are more sensitive to small pressure changes. The bellows element can be considered as an extension of the corrugated diaphragm principle. It may be used for high, low, or differential pressure measurement. Typically, the bellows element is used to measure pressures like the output of an aircraft low-pressure fuel booster pump. The Bourdon tube is the oldest of the devices used for sensing pressure. The element is essentially a length of metal tube with an elliptical cross-section and shaped into a letter C. One end of the tube is sealed and called the free end. The other end is connected to the pressure source and fixed. When pressure is applied, the tube tries to straighten. This movement is magnified to drive an indicator pointer. The Bourdon tube can be manufactured to indicate high or low pressures, but it's normally associated with higher pressures such as engine oil pressure. As well as the actual pressures, Warnings can be displayed to the pilot by pressure-operated switches. These switches can operate for low, high, or incorrect differential pressure. A differential switch or gauge is subjected to pressure on both sides of its sensor.